So, as you saw on that one worksheet, you had a chance to do a problem on velocity and vectors, and they're the infamous boat problems or the river problems, and it's a struggle for a lot of physics students. So we're going to go through some examples, and at first you might see that it's a right triangle, and you may just want to do geometry, which you can. However, it is very, very wise to do these problems thinking x's and y's, and then doing everything in the x and everything in the y, kind of like we've been doing this chapter. And there's a reason for it, and that is sometimes this is not a right triangle. And then if you only know how to do this with a right triangle and with sine cosine, you're going to be out the window. Okay? So yes, this is a right triangle in this picture. It's not always a right triangle. Okay? So let's talk about what is influencing what. And let's read the little problem and try it, and then we're going to work our way and see why this is in this chapter. All right. A boat can row at a speed of 1.3 meters per second with respect to the water. Remember that relative velocity thing we talked about before, like if you're walking on a train and the train's moving and all that stuff, right? You can walk at a certain speed, maybe 5 miles per hour, but if you were on a train, right, you might be going, 55. Yep, grab it. All right. So in that same sense, when we talk about a boat speed, it is with respect to water. That motor can only push against the water. Okay? A plane can have an airspeed. All right? And we understand, right, that even though you have a plane that can fly, or let's do a bird that can fly, let's say 20 miles per hour, if there's a headwind of 20 miles per hour, is that bird going to be moving? Not relative to the ground, it's not. And so we have to think about air speed, water speed, versus ground speed or shore speed. Okay, so there we go. So that we know is with respect to the water. If you want to cross a 62-meter wide river, okay, and it has a current of 0.60 meters per second, and you want to land directly on the other side, what direction must you row? What is the boat's velocity with respect to the shore? When will the boat arrive on the other side? So there's lots and lots of questions there. Okay, so we know to look at, normally, this is all whatever. I normally make my rivers going right to left, but it doesn't matter. It just depends on the problem. And we always do upstream, downstream, so it actually doesn't matter when you answer it, as long as you're consistent. Okay, so I have my river going in this direction, and again, that would be 0.60 meters per second. All right, and in fact, right, we can see that here, right here, that's 0.60 meters per second if I do some vectors. If I headed straight across, everyone knows, right, the boat would have dragged me downstream. Well, we don't want to do that, or whoever this problem and this person wants to just go straight across. So what you should do, right, if you head what we call upstream, people go, what's upstream? I'm so confused. Upstream is, do you understand the river starts somewhere high and goes somewhere low with gravity? I know. So this is upstream, where the river comes from, and this is downstream. Okay? I will have people miss points because they can't do that. All right? So, and this isn't me. This is, this is what people talk, river talk, and it's what we do in every textbook. I have students doing right now Michigan Virtual, and they have the same kind of problems, same kind of stream problems to be tortured by if you take online physics. So, okay, so we're heading like this. Okay, and we want to head directly on the other side. So here's another cool vector thing. The velocity of this is vector. The vector of the velocity of the boat with respect to the shore, that's what this means, boat to shore, plus velocity of the water to shore. Do you see this? This is water to shore. What will that equal? Boat to water, water to shore, equals BS. All right. So boat to shore. Oh, it's not what you were thinking. Boat to shore. Okay?
So first one. Yeah, isn't the first one boat to water?
Oh my gosh, what is my problem? I'm sorry. I was so focused. That made no sense, did it? I'm sorry. Boat to water, water to shore makes boat to shore. Now, when I have these additions like this, these are vector additions. This doesn't mean if this is 5 and this is 2, this is 7. This isn't regular addition. This is in this picture addition. So if I have this vector and this vector, it adds to this vector. And that's what we're interested in. Okay. All right. So how do I get it, though, so I go straight across? What do I know? Let's think x's and y's. What do I need? I need so we get straight across. What do we know about my velocity in the x direction? This is x still. Let's just call that x. Okay, what do we know about my velocity in the x direction overall? My overall velocity in the x direction, do I want to go left or right? So I need that to end up being 0, right? I need, how about net? Yeah? If you want to say it that way. Okay, I need it to add to 0. So I know people already have the answer here, right? What's going on. So you know, right? So what is going to happen here? So in other words, you're out of this, right? We know our velocity of our boat with respect to water in the x direction, right? Velocity of boat with respect to water in the x direction. And what else? What else is in the x? The current, right? The velocity of the water with respect to the shore in the x direction, that has to all equal 0. My x's have to undo each other, yeah? So however much the river is going downstream, my boat must be producing that same velocity upstream. Okay? Right? My x of my boat and my x of the water should equal 0. So, how do I find this out? How do I ever find the x component? X component, right away in this class you need to spit out what? How do you find x component every? Right? We need cosine, v cosine angle. So what is our v? So we know it's 1.3 cosine. You go, well, we don't know this. I know, but we can solve for it. All right. And then, what about, let's do this proper. I know people already know. How much is the river going in the x direction? It's 0.6, but it's this way, so it's negative. But let's prove that it's negative. So let's just put 0.60, and then we're going to do cosine. What way is it pointed?
Negative 180.
180. Is everyone with me? Isn't this 0? This is 180. Okay? All right. What is the cosine of 180? Negative 1, so that we, I'm just proving mathematically how we know the river is, 0.60 to the left. We need this to be 0.60 to the right, in other words. But let's just do this. Let's rewrite this. Okay, so now we solve. So when we solve, right, I'm going to bring this over to the other side and say 0.60 equals 1.3 cosine angle. Then I will divide, right? So I'll have cosine angle equals 0.60, right, over 1.3. But what do I do now? Inverse cosine to both sides, which leaves me with my theta or angle. And then I'm going to do that. And the magic of math, it's 62.5, but I just have 2 sig figs, so 63 degrees. Okay, now you will be upset. Okay, everyone's good with this? People, you did a lot of work for this very simple problem where it's a right triangle. I know, but if the problem is harder and you follow the same methodology, you could still do it. So we're proving the x component of the one and the x component of the other. If you're not going to go upriver or downriver, needs to equal this. Okay, and so our angle to make this so is 63 degrees. But that is not how, when we say what direction must you row, in river speak, that's not how we answer. Do you know how we answer? I want to know what is our angle upstream. Okay? All right. Now, didn't we learn if we use cosine and sine, it always gives you this from a horizontal? This is 63 degrees. So, if I want to do this proper speak, I need to do what? 90 minus 63, right? And so we get 27 degrees upstream. And you go, that is, you could use different expletives for that, but that is what the textbook, online physics, the world speaks upstream and downstream. Okay? All right. That's the first one. What is the boat's velocity with respect to the shore? So we want to know, how is it moving now? And that would be this. Okay? And do you realize what that is, really? So the velocity of the boat to shore, is really what? Of this. Is this helping it get across?
No.
That has no y component. That's not doing anything to your velocity vertically. So what's the only thing lending to your vertical velocity? Is what? The boat with respect to water, which way? Y. Now we got a lot of letters there, I know. So the boat to shore in this case is just your y velocity. And so how can we calculate that? The same way we find the y of anything. So we need the y of this. The y of this. And so we have 1.3 sine. Okay? Sine of what? Now I've got you so confused. What does the calculator know the angle? Does your can you put in upstream and downstream in your calculator? No. So you got to tell it, the calculator, always from the horizontal, right? From the positive x. So we're going to put 63 there. Okay? And when you do that, the velocity of the boat with respect to the shore, the speed at which it's crossing, is going to be 1.2 meters per second. Okay? This is 1.2 meters per second. All right, we're in the home run for this problem. Now we want to know the last thing. When will the boat arrive on the other side? Some people will do this super complicated, and you don't have to. Some people go back to how the boat is going and figure out the distance the boat is going, and then figure out the time to go at that angle, some weird We don't need any of that. The only thing getting the boat across is this. We're going vertically or across the river at 1.2 meters per second every second, right? So every second we go 1.2 meters is what I meant to say. And so, right, we know that is a constant velocity. So we know velocity equals, right, displacement over time. And we know this is 1.2. And we know this is 62. And so we can solve for time, right? And if you do that, you get 52 seconds. Okay? So when you do a problem, just every time, figure out what in the x and y you are doing. Okay. Let's just look at this. And again, let's see what's different about this case.
It was different.
All right. All right. There are different. These are both right triangles I'm doing, and it doesn't have to be a right triangle. Okay. So, what have I done now? What is the difference in this problem? This person just headed straight across, right? And they said, river, do what you will. Okay? And so they went like this, and they got pulled downstream. Yeah? Okay? Okay. So tell me, if you did this, what about your speed across? Is it slower or faster? Why is it faster? Okay. Two things. One is your actual speed across the river. It has nothing to do with your downstream. But your speed, didn't you take all your motorboat speed or your paddle speed, whatever it is, and all of your effort is in the y direction? You didn't waste some of it going in the x. You took all your effort. So whatever it was, if it was 1.3, now all 1.3 is going north. Before that wasn't the case, right? Okay, so your speed across, right, is faster, right? You're going to get across to the other side faster. All right? Okay. But you arrive where? You're going to arrive downstream. Yeah? All right. So you may not be where you wanted, but it depends on what your goal was. Was it to cross the river as quickly as possible because there's alligators? You should do that. Okay? All right. All right. What about the velocity of the boat relative to the shore now? That's this one. Isn't this the sum of this and this? This was kind of like the problem I said you had a projectile, and at the bottom I wanted you to figure out its overall velocity, and it had an x and a y now, and not just only the x like it started with. Same thing here. This was what the boat was doing, but the river was making it move extra. So this is your overall velocity of the boat to shore, right? So it is greater, right? Okay. There are going to be cases where we could do the other one where it isn't a right triangle. What if you go like this, but the stream is greater, Then you could still be pulled, like you didn't set an angle enough, right? And the stream is greater, you could still end up going downstream, right? But not as much. How should you do that? Then then you need to figure out you have an x velocity, this has an x velocity, and you need to see these would be subtracting from each other, right? And you'd have some left over. And then that would affect it. Your y velocity is always what gets you across the stream. The stream never helps or hurts you getting across. Yeah? The more and more you head upstream to try to counteract it, then you're going to go slower and slower across. But the key is your y is to figure out how long it takes to get across the stream, and knowing over your overall x will determine either how much upstream or downstream you're going to land. Okay? All right, boats. You're going to have some boat nightmares.